So, welcome to the next part of my world building guide series for creating an Earth-like fantasy world, and this is part 8 to be exact, and I will have the playlist linked below if you want to start from the beginning. And before we get started, I will apologize. My children are still not asleep, so you may hear them hollering and shouting, and we're gonna just ignore it. My husband is on duty, so it's fine. But yeah, so in the last part, which you should see here, we classified all of our climate regions on our global map, and I will say, climate has a tremendous impact on culture, dictating where there will be droughts, the seasonality, how much water is available for agriculture, what crops and other resources are available. But there are more weather events that can provide a very unique inspiration for culture and provide a bit more color and pizzazz to our worlds in a fun way, and also impact, culture, history, mythology, especially. This part of the series is a sort of side quest. We aren't going to build off of it in future videos, but it still can be important, and I think it'll sort of be a pick and choose what might make sense for your world or the areas you're really world building type of thing. But we're going to talk about severe and interesting weather events. So things like hurricanes, tornadoes, the aurora borealis, fog, blizzards, that sort of thing. And everything we're going to talk about could really be a video of its own. And some of this stuff is incredibly complicated, and I think you'll sort of get a feel for that as we go through this. And I don't have the necessary number of PhDs to fully be able to come up with a complete, detailed, exact guide for this, but I came up with a lot of patterns that you can follow, and it should be enough to sort of give you a general idea on a global map of what goes where. And if something's going to be particularly important for your world, then you're just going to have to look into it and maybe do a little bit more research, or kind of just go with a slightly more artistic application and more of a pattern kind of thing, which is what I'm going to be doing here. So we're going to go through each of these sort of weather events one by one and create a number of maps. Some of these things will be on the same map, some will be on different maps, some will be seasonal and some won't be seasonal. It'll really just depend. But I tried to make this as clear as possible. You won't always see both seasons reference maps and stuff like that in here, but I tried to fit what I can. So let's get started. So first we're going to be talking about thunderstorms. And in theory, thunderstorms are possible everywhere under the right conditions, but there are going to be certain areas that will have them more often because there are certain conditions, certain things that make them more common, more likely to be powerful, that sort of a thing. And so in general, thunderstorms will tend to form as warm, humid air rises into cold air, and this air will then cool and drop, warm again and rise again, creating something called a convection cell. And the number of convection cells will determine how severe or long-lasting a thunderstorm is. And if we look at our air circulation map, the most likely place for these to occur would be where we have low pressure belts and different air masses meeting near the surface, which is mainly going to be our ITCZ and our subpolar low belt. And remember, the global surface winds are actually a reflection of large convection cells that wrap the globe in belts. So just when we're thinking about all these convection cells, just kind of think about that, right? So single cell thunderstorms are going to be the least severe and the most common. These thunderstorms will be quick, maybe an hour. They will have maybe rain, some lightning, some hail, and these are typically going to happen during the summer. Multi-cell thunderstorms mostly form along warm or cold fronts, and these can last a lot longer and cover pretty huge areas. Supercell thunderstorms are very large and last for hours, and they are rare but can produce large hail and even tornadoes. And now, what is the big thing that fuels all of these? Convection. And this is a main likelihood factor wherever you have large land masses that can heat up during the day, that will create convection. And this is why you will also see that thunderstorms are pretty unlikely out at sea due to the fact that the sea doesn't really warm at the same rate as the land does, which we've talked about in numbers of videos. So, most thunderstorms, like we mentioned, are going to occur along the ITCZ. due to the warm moisture, the surface heating, and the trade wind convergence. Large land masses with high moisture around the ITCZ will be even more likely to have thunderstorms due to those regions. The next likely place for thunderstorms will be wherever the warm westerlies and cold polar easterlies mix over warmer land. This is normally the subpolar low belt, but remember that you need to have enough convection, surface heating, for thunderstorms. So a static subpolar low belt is typically going to be too cold and too dry for many thunderstorms. However, the subpolar low belt is not static. The edges will wave and grow more extreme until some of the low pressure breaks free. So the areas below your polar vortex region, which we will also talk about more later, where there are large land masses and warm air coming from the westerlies, you will see frequent thunderstorms, particularly in summer. Another place you can see thunderstorms would be areas with monsoons in the warm seasons, where you will have moist offshore winds and warm land masses. And for the most part, you can just assume your wet summer monsoon seasons will also include thunderstorms. Just know that. Mountains will also affect the likelihood of thunderstorms. At a smaller scale, thunderstorms will be more common on the windward side of mountains where warm air blows up the mountain. If this is also combined with being near the equator, so a warm landmass, with moist air blowing from offshore, you could see almost daily thunderstorms. Polar regions are going to be the least likely to have thunderstorms just due to the extreme cold leading to insufficient moisture. If you have east-west mountains parallel to your wind belt, this will keep the warm and cold air masses from mixing too much, and you will also not see as many thunderstorms. So let's move on to mapping our thunderstorms. So on each of your seasonal maps, and create one for each just for storms in general, and you can do this in pencil, you can do this on layers like I did this time, which is very fun. I'm enjoying it. The whole Photoshop layers thing, it's fun. But we're going to map out three main things to start. Low pressure areas from our atmospheric pressure maps. And you can see that I have these circled in pink here. So these are low pressure areas from our atmospheric pressure maps other than those above our subpolar low belt. And this should already account for the area around the ITCZ and the equator side of the polar vortex. If it doesn't for some reason, you can include those too, but that's, again, circled in pink on this map. And then large land masses that have warm or warmer seasons. And this is, I think, yes, blue. This circle will represent the warming capabilities from the land to create convection. And then in green, I have windward side of mountains that run more north to south, perpendicular to those wind belts. And then in, let's see, yes. So then if you reference your air circulation maps for the summer hemisphere for each hemisphere, you can draw red and blue arrows. The red arrows will represent warm offshore, aka humid winds, blowing into those circled areas, and blue arrows to represent colder winds blowing into those circled areas. And you don't have to be too granular about this. Again, this is a global map. We're really only looking at large-scale effects. So like, if it's like just a little bit, just skip those, right? So you can see here on this map, I have some cold winds. These are all mostly coming from the polar end, and warm winds coming from the equatorial side on here. So now we can go through and map the chance of summer thunderstorms. I use a scale with 5 levels, and I prefer low and none to have no color or markings. You can give those a color if you prefer. It's whatever works best for you. But we're going to start with low or none and basic thunderstorm chance. And this is going to be similar to how we did precipitation, where we just sort of build it up with each sort of effect. Will increase the likelihood and severity of the thunderstorms that you'll find there. So basically, there are going to be low or no chance of thunderstorms anywhere there isn't a basic chance, which is going to be polar regions, dry or cold, flat, deep continental interiors. So what I did is I did basic first, and then anywhere that was left as low or none, I left as low or none. And so basic would be everywhere between your subpolar low belts that gets at least warm and isn't arid year-round, and anywhere else that was circled in the previous step. So you can see here, all of the yellow is basically anywhere that is a basic chance, and the white areas are the low chance. So next we're going to do moderate and severe. And moderate is going to be all of our circled areas from above that have red arrows blowing into them. So you can see on here, I increased the color to orange anywhere I had those arrows blowing into them, or anywhere there was enough overlap. And then severe is going to be areas with multiple circles around them, particularly areas where you have both red arrows and blue arrows colliding. And this is where if you have anywhere that has multiple circling arrows but doesn't necessarily have, anywhere that should be severe that has multiple circles, especially areas that don't have blue and red arrows, then I would just make those moderate and not severe. Try to be a little bit more stingy with this. And then the next color, the last one, is the severe tornado risk, which we will do in the next section, but that's basically areas that have the potential conditions for supercell thunderstorms and extremely destructive tornadoes. All right, so tornadoes. Tornadoes can form where you have supercell thunderstorms, which we already talked about. Specifically, you will mainly see these 30 to 50 degrees in the Ferrel cell between your subtropic high and subpolar low belts. Just like you have a small chance for thunderstorms just about anywhere, there's a small chance for weak tornadoes in most places too. And typically these will be rare and small, so we will only be worrying about places with a high risk for very destructive tornadoes. We will want to look at some of these similar areas that we looked at for thunderstorms, places where we are more likely to find super severe storms. So we are going to map tornadoes on one map, but note that these will be occurring in the summer months in that hemisphere. So for the northern hemisphere, you'll be looking at that hemisphere's air circulation and thunderstorm map or storm map, and the reverse for the southern hemisphere. So compare your elevation and air circulation maps to find the areas that are fit for supercell thunderstorms. This will be the severe areas of your thunderstorms maps, but to be specific, between your subtropic high and subpolar low belts, roughly 30 to 50 degrees north and south, where you will have flat plains where cold and warm fronts can meet. Look for warm offshore winds flowing over lower plains towards higher altitudes where there will be cold, dry air. And the severity will mostly be based on how contrasting the moist surface air and the dry, higher altitude air are. So you will see a higher chance in areas with large, flat plains with lots of moist, warm air, right next to high mountain ranges with lots of cold, dry air blowing from the mountains towards the plains. So look at the weather map that we've been working on and add severe tornado risk in mainly these areas. All right, so fog. Fog is a bit of a weird one. It's essentially just low-lying clouds, right? And it can occur when air is quickly cooling at the surface and the air is humid. And there are many different types of fog and many ways it can form. But we're only going to focus on some of the most common types and some of the ones that are easiest to map on a global scale like this. So because our air circulation and ocean circulation and other factors are seasonal, it is best to mark both. I like to do this on the same map, so I'll have a high chance of fog in summer and winter as different colors in the key. And now we're going to mark these areas based off these sort of factors that you see here. All of these are going to cause a chance of fog. So at sea, where moist air encounters cooler waters, along coasts where cooler air blows over warmer waters and humid air, at sea or along coastlines, around areas of major upwelling, around warmer bodies of water and high pressure areas, in mountainous regions and valleys in the windward side of mountains, and where warm air flows over glaciers. We're going to go through these mostly one by one. All right, so first, we're going to be looking at the sort of sea, out at sea, off the coasts, where moist air will encounter warmer waters. So you're going to look at your wind current and ocean circulation seasonal maps. I only have the northern summer hemisphere ones here. For areas with cold shores and onshore winds coming from the equatorial direction, aka warmer winds, So you can see on these maps, I circled the areas on the wind currents map where you're going to see these onshore winds, and the seasonal ocean circulation maps where you have these cold shores. And you can see on the map how I colored in those regions offshore, not on the shore, but like right offshore along these areas. Okay, so next, we're going to look at coasts where cooler air blows over warmer waters and humid air. And you're going to look at, again, the wind current and ocean circulation seasonal maps for areas with warm shores and onshore winds coming from the polar direction, aka cold winds. This is sort of the reverse. And again, I have these sort of circled in the bottom for the northern hemisphere summer ones, and then you can sort of see those reflected on the map there. So next we have at sea or along coastlines with areas of major upwelling. And you can see I sort of have both of these ocean circulation maps down here at the bottom. I've circled the areas of upwelling for each season, and you have those added to the maps up above. And then you have around warmer bodies of water in high pressure areas. So I have my atmospheric pressure maps, and you can sort of see in these high pressure areas where they're sort of the most concentrated. Along the coast, I sort of have them circled and then added to the map up above. Next is going to be in mountainous regions in the valleys and the windward side of mountains. So mainly you're going to see these in the valleys and the windward sides of the mountains, but that's too granular for this stage right now because this is going to be more of a smaller scale fog effect, but we can sort of give this little wavy line to indicate that that's where these areas are going to be. So next we have where warm air flows over glaciers. And you're going to look at your physiographic region or your climate region map where the glaciers are, which is going to be your EF sort of area. And then look at your wind current map to see where warmer air would be flowing over them. So you can sort of see here, I have circled one main area at the bottom for the northern hemisphere summer at the bottom there in orange, where you have warmer air coming up over the glaciers. Hurricanes. These great storms are tropical cyclones and are called different things depending on which waters they originate in around the world. Hurricanes, typhoons, cyclones, they're all the correct term, but I'm going to call them hurricanes for the purpose of this guide because that's what I'm used to calling them. So hurricanes are large, powerful weather events that pull the heat out of warm tropical waters to fuel their violent paths across the ocean. A hurricane is essentially a moving low pressure zone that pulls the warm ocean air up and causes air to blow in, cool, and rise to form the great clouds that you see with these, like in this map. You know what I mean, this picture. In order for a hurricane to form, you need a low pressure weather event, warm tropical waters, and the right wind conditions to allow for that closed, low-lying circulation. The tropical storms that hurricanes can form from will usually originate along the ITCZ, which is low pressure belt. But due to the Coriolis effect, they can't form within 5 degrees of the equator, which is very interesting. So the Coriolis effect is the deflection that is caused by the rotation of the Earth. And we have already indirectly discussed it when mapping our air circulation maps. So in the northern hemisphere, on the northern side of the equator, currents are deflected to the right and then to the left in the southern hemisphere. And this is the effect that gives a counterclockwise rotation to low pressure areas in the northern hemisphere and clockwise rotation to the ones in the southern hemisphere. So right at the equator, the Coriolis effect is absent. So we lack the force required for creating the rotation needed for hurricanes. Another important thing to note is that hurricanes can't cross the equator, right? Because then they would be sort of flipping rotations. It has been argued that it is theoretically possible, but it has never happened in recorded history. So maybe, I don't know, write a cool book on that or do research. That's very interesting, but it has never happened, so we are not going to include it in our mappings. But if a hurricane forms in the northern hemisphere, it will travel west and then eventually turn north towards land with the prevailing wind. And if it forms in the southern hemisphere, it will travel west and then turn south. So, if you connect all these patterns, we will only have hurricanes forming in tropical waters along the ITCZ during summer in that hemisphere if and only if the ITCZ is actually in that hemisphere at the time and isn't too close to the equator. So specifically, we will look for that sweet spot between 5 and 20 degrees from the equator. So if you look at the Earth maps of the ITCZ in July and January, you will clearly see one of the main reasons why hurricanes do not form in the South Atlantic Ocean nor the eastern part of the South Pacific Ocean due to these factors. And the exact hurricane season will vary a bit in different parts of the world, but you tend to see peak seasons to be late summer and into fall. And because hurricanes are fed by warm waters, anywhere you have cold waters, either through cold water currents or cold upwelling, hurricanes will be slowed, and this will help protect the coasts from hurricanes, or at least weaken them, right? And this also means that if you have oceans along the equator that are very open to polar waters, they will not be warm enough to form or continue feeding hurricanes. And this is one of the reasons you don't really see hurricanes hitting South America in the southern hemisphere, because the South Atlantic gets too much cold polar water. In the northern hemisphere, the polar waters are mostly isolated from equatorial oceans by land masses, meaning this water is a lot warmer, hence significantly more hurricanes found there. And we're going to look for similar things on our maps too. Okay, so mapping our hurricanes. So for each span of ocean at 20 to 50 degrees from the equator, we will first consider if the conditions exist for creating tropical storms that could produce hurricanes, and then we will determine if those storms would be able to build into strong hurricanes and reach land in a destructive pattern. So look at the eastern side of each ocean in this area and determine is the ITCZ in that area during summer? Is the ocean sufficiently warm enough to feed a hurricane, so ocean isn't fed by large amounts of cold polar water? And if both of those conditions are met, then trace the paths of these storms to see where the hurricane could reach land. In the northern hemisphere, it'll travel west and then eventually turn north towards land, and the opposite in the southern hemisphere, but still traveling west, it'll just turn south. Yeah, so not quite the opposite, but you get the picture. And if the oceans along the coast are particularly cold, this will reduce the strength and reach of the hurricanes, and this could be due to currents or significant upwelling. So you can see here on this map in the blue, that blue line I have, this is my ITCZ in each of those seasons. So you see the summer hemisphere one down below, where the summer hemisphere and ITCZ are in the northern hemisphere. And then you can't see that map right now, but the one on the bottom is where it is when it is summer in the southern hemisphere. And so I sort of looked at these and figured out like how much are we going to see here, and you can sort of tell here there's not enough ocean width between the two sides of my map, right? So like wrapping around, because those are very close together, so there's not really enough room for hurricanes to really grow. So I'm really looking at the center of my map, and you will see that I have land masses that are, at least to a pretty significant effect, blocking off some of that really cold polar water. So I'm going to see pretty equivalent hurricane chance in both my northern and southern hemispheres here. And you can sort of see that at the point that they start getting towards land, I'm starting to draw those little lines that show the potential paths, similar to the map we saw like 2 slides ago. And I didn't draw the ones all out to sea because I wasn't really focusing on that, but you can sort of see here like where these paths would go. And which coasts are going to have the highest risk of them. And yeah, I think it's very interesting. And as the ITCZ moves, there's a chance that you're going to see them in different areas, but this is going to kind of be the main area, right? The main area of risk. Okay, so let's move on to winds. And air on the planet is never stagnant, as we've talked about many separate different times. It is always moving. And there are 3 main types of winds. There are primary winds, which think prevailing winds, or those created by the rotation of the Earth. We really cover those a lot in our air circulation maps. Secondary winds, and these can change direction seasonally or periodically. And tertiary winds. These are mainly local winds caused by pressure and temperature differences or changes. We haven't really covered those so much. Here's a list of some of the primary and secondary winds. The primary ones you're already familiar with, right? Tropical easterlies are the trade winds, the westerlies, the polar easterlies. And then in our secondary winds, we have monsoons, we have our sea breezes, which are essentially the onshore winds that we mapped, the land breezes, which are the offshore winds that we mapped, mountain breeze and valley breeze, which is just wind patterns that happen along mountains, right? Local winds. There are a ton of local winds around the world with their own names and features based on the wind patterns, temperature, and geography in those local areas. Some of these are the Chinooks of the Rocky Mountains, the Mistrals in the Rhine Valley region of France, the Föhn winds in Switzerland, Austria, and the Alps, and the Mango Showers in the Deccan Plateau of India. I doubt I named all those or said all those names correctly. And the importance of these local winds should not be discounted, as they can have a very, very large impact on the way of life and the agriculture in these specific regions. So let's go back to strong winds. So when it comes to our prevailing winds, the strongest winds are going to be where we have the greatest temperature difference between two locations. So these are going to be our polar subtropic jet streams and our subpolar and subtropic wind belts. And you can see on this map here, we have our polar jet and our subtropic jet. So we're mainly going to be looking like 30 and 40 to 50 degrees north and south. And these are west to east blowing winds high in the atmosphere. So you will also see strong winds where high and low pressure zones are very close together. If you look at the global offshore wind speeds map, this should give you an idea of where they are strongest. And if you'd like, you can map all these winds on your air current maps as being stronger winds, as they will be fuel for marking many of our extreme winds next. We will be mapping some of the areas where we will find particularly extreme winds. And there are three main forces we will discuss that will affect the speed of winds. The first is friction. The more the Earth disturbs air circulation, the more it will usually be slowed down. So the furthest air can go without hitting resistance or experiencing friction, the faster it will be. And the more friction, the slower it'll be. So winds that are funneled, that's the next force, through mountains or rugged terrain instead of having to go over them will also be intensified. Think of things being pressed through a funnel and sort of speeding up as they all have to go right through that funnel. And then the third force we will discuss is temperature. Hot air rises while cold air sinks, and in certain conditions, this can cause some of the strongest winds on the planet, which we will get to more, I promise. Surface winds travel around the surface, and as land increases in elevation, wind will lose some of its strength. The more irregular that increase in elevation, the more hills and valleys, the more wind loses even more of its strength. So wind can be extremely fast across the ocean, free from friction other than from the water itself, and across large flat plains. So the more irregular and hilly or mountainous an area, the more the winds will be disrupted. So what we're doing here to start is we're going to color in any areas for each season where we have large flat plains or islands where strong prevailing winds blow uninterrupted. And for the most part, you can see here I'm looking at my wind belts, and I have those mapped on the bottom for the northern hemisphere summer, where you can see that I've circled along those belts anywhere they meet land where it is an island or large flat plain. Where quick moving winds, the jet streams, have been traveling uninterrupted over the ocean collide with the coast, we will see strong sea winds, even if the land itself is rather mountainous. So low-lying islands that are in the paths of major wind belts will frequently have very strong sea winds. The island of Orkney, which is one of the windiest places in the UK, is relatively low-lying and is exposed to both the Atlantic Ocean and the North Sea. The island has an average wind speed of 38 miles per hour and frequently experiences gale winds of close to 100 miles per hour, getting as high as 125 miles per hour. So I went there on my honeymoon, and on our first day, had very little wind for Orkney. And I still had a gust of wind below my glasses, straight off my face and down the street, and that wasn't even a windy day at all. On the next day, it was a little bit stronger winds, still not strong in Orkney standards. Just walking was a challenge, especially if we were near the water. I think we were trying to go see some sort of like Neolithic site or something. And I remember just walking and leaning in, and we had like our like rain jackets tied up so tight, and like the whole hood of our jackets were just completely blown up, and just like trying to walk through it. There's birds that were just flying, hovering in one space, just trying to make traction, but they couldn't move forward because all they could do was like keep up with the wind. It was intense. But another note on islands with frequent strong sea wind is that the wind will also carry salt, affecting the vegetation in the soil here. So keep that in mind. So you can map coasts where strong prevailing winds collide with the shore, and low-lying winds where strong prevailing winds flow over them. So, funneling. Where winds are funneled together, they tend to intensify, as we mentioned. So anywhere on your map where you have strong winds being funneled through a low-lying region between two mountains, you're going to see this. Now keep in mind that the direction of the wind and the angle of this funneling matters, and also the size of the funnel will impact the strength of the winds. The more focused they are, the stronger they get. So for the most part, on a global map like this, we don't know where those areas are going to be. So that's going to be like a chance in these regions, but you'd have to like look at your local maps or your regional maps to determine exactly where these winds are going to be. But a fun example is in the Rhine Valley of southern France, the Mistrals are winds that blow the clouds and dust from the air and leaving the region particularly sunny and the air particularly clean. So there's a high pressure zone in the Bay of Biscay and a low pressure zone in the Gulf of Genoa, and these create strong winds that blow southeast into France. They're further magnified by being funneled through the foothills of two mountain ranges, the Alps and the Cevennes. And these mistrals had a large impact on this area, from agriculture to culture. The winds even affected how the original people that lived here tens of thousands of years ago built their fireplaces and homes to just protect them from the winds. And these winds are not extreme compared to some of the others we will talk about. The mistrals can reach speeds faster than 56 miles per hour. But still, like, you have a region with beautiful clean air, a beautiful sunny region, you know, like this, that's something that affects an area, you know, and really says something about the type of cultures and societies that you're going to see in that area, especially compared to other areas in the region area, you know. So here you can see on this map, and this is the winter solstice in the Northern Hemisphere map, but I basically circled the mountain ranges where I am seeing wind currents that are blowing sort of perpendicular to these mountain ranges where they could be funneled through. So basically anywhere there could be gaps between mountains leading to flatter land. On to a very fun one, katabatic winds, which are so freaking cool, let me just tell you. But this pulls in temperature inversion, which is a big factor for the winds in the coldest parts of your map. So in most places, the land is going to be warmer, and the further up you go, the land will get cooler, or the air will get cooler. However, in extremely cold areas, particularly those covered in ice sheets, right at the surface, it is so cold that the air there will actually be colder than the air higher up in elevation. So as cold air is denser than warm air, above the ice sheets, the air is always cooling, right? So it's lowering, sinking, cooling down, continuing to sink, creating this effect. And so the dense air will flow down the ice sheets and towards the coast, creating something called inversion winds. With uneven terrain, as is common in these areas, remember how glaciers and ice sheets can carve the land, right? These winds are channeled like water to streams, creating very strong katabatic winds. The best example, the Commonwealth Bay in Antarctica is considered the windiest place on Earth with average wind speeds of 50 miles per hour, and the katabatic winds regularly reach 150 miles per hour. Even 200 mile per hour winds aren't uncommon. For comparison, Category 5 hurricanes are classified by sustained winds of at least 157 miles per hour. So you are talking about sustained, not uncommon winds that are Category 5 hurricane level. That's crazy. Like, that's a real thing. That's crazy. But yes, so Look at your map at the land around your ice sheets where you're going to have cold, dense air flowing down towards the coasts. And this is basically anywhere where you have rugged terrain, right where you're seeing a decrease in elevation on the edges of your like ice sheet. So you can look at your EF climate zones where it's pretty rugged terrain, where you would have that decrease in elevation. All right, so let's move on to sandstorms, dust storms, and blizzards. These storms are going to be where huge walls of dust, sand, or snow are blown by strong winds, usually from thunderstorms in areas that are dry and flat. And while these can be very short events, they can cause very big problems. Not only can these storms take people by surprise and cause visibility issues, but dust and sandstorms can require a large amount of cleanup and impact breathing conditions. People with asthma and other lung conditions will be the most impacted by the severe drop in air quality caused by these storms. And there are also diseases that can be transmitted by them, carried by the particles that can remain suspended in the air for days. So meningitis and valley fever are two such examples. And blizzards can block paths and roads, isolating people in their homes, make it so cold that people can starve or freeze due to being just trapped. So any people that live in areas with a high risk for these kinds of storms will need to have ways to mitigate and deal with their effects. So look at your strong winds and storms that we've already kind of talked about and mapped out, our elevation maps, our aridity maps, and mark anywhere that meets this criteria as having a large risk for each of these three types of storms. Dust storms and sandstorms are mainly going to occur during summer, and dust storms will occur over plains and sandstorms are over deserts, which makes sense. Is there dust or is there sand? And these both will occur where there is large, flat land, where it is dry and devoid of many trees or lush vegetation. So we're looking at areas that are arid on our aridity map in summer. And then potentially storm risk in that area is moderate or higher would increase your chances of this. So you can see here at the bottom, I have my climate regions and my aridity maps. And you can see that the little green and yellow sections on my dust storm, sandstorm mapping sort of correlate with areas that fit all of those conditions. And I didn't actually have a lot of dust storms on this map because in the regions that I would mostly see this, I actually have a lot of desert. So it's possible that pockets of these would be dust storms and not sandstorms, but it was kind of hard for me to tell at a global scale, so this is what I have. So then blizzards are mainly going to occur in winter, surprise, surprise, and can be found basically in areas with tundra or other cold snow-covered areas because you need lots of snow for blizzards, and then strong winds. So I've sort of circled the climate region section that would be cold enough for this, and I also have them listed out here. But you can see on the map, I colored them this light blue color because it's an icy cold blue, But anywhere with a big risk for blizzards. So next, we're going to move on to northern lights. And I will be calling these northern lights as they are called in the northern hemisphere, but they're also southern lights in the southern hemisphere. I live in the northern hemisphere, so I'm used to calling them northern lights. It's fine. So while these are less of a weather event, the northern lights are still very cool and sort of fit in with how we're sort of mapping these other ones here, and they can have a really big effect on the people that live there, mainly from like a cultural perspective. So the northern lights, or the aurora borealis, is an atmospheric phenomenon? Yeah, we'll go with that. Causing beautiful waves of colorful lights to dance across the sky. And they are caused by the planet's magnetic field deflecting particles from the sun towards the poles. And civilizations in areas where they can see these lights come up with many different divine myths involving them, so it's something that you can be very creative with, and I recommend you Google them because they are really cool. So these lights are mainly found in something called the auroral oval, which is roughly 60 to 70 degrees north and south. And this oval is not consistent and can meander a bit, and the lights can be seen at lower latitudes if there are particularly strong solar storms. We're not going to get into that. Yeah. So you can see here on this map, I've marked the rings between 60 and 70 degrees north and south in both hemispheres as having frequent northern-southern lights. These are going to be areas where these are kind of a staple in these regions. Ignore the other colors on here for now. The Polar Vortex. And I keep saying that I'm not going to get into this much, and then I keep just like lightly bringing it up because it is surprisingly impactful. But there is a video that does a really good job explaining it by Amit Singh Gupta, which I will link down below. Essentially, the north and south poles are high pressure zones in the lowest level of the atmosphere, but in the next level up, you have the polar vortex, which is a low pressure zone. And so the polar vortex is bounded by the subpolar low pressure belt, which is the strongest in winter and weakest in summer. Because of this, in the winter, you will have a fairly straight or consistent subpolar low belt. You can sort of see that on this map in A, that's sort of what it looks like. But in summer, when it is weaker, the polar vortex will sometimes expand and weaken. And this is not, again, consistent or easily predictable, but we can mark a general area of our map where you will tend to see breakthroughs of the polar vortex. And when the polar vortex breaks, you will see cold waves of unusually cold Arctic air moving into lower latitudes that are usually milder. So these breaks can reach nearly to the subtropic low belt. And this happens about every other year, causing record temperature drops and the potential for large snowfalls in areas that don't normally experience this. And again, you can sort of see this in the maps. In B, they're weakening, and then in C, pieces of it sort of branch off into these like, kind of cold waves that travel into the lower latitudes. On Earth, North America experiences these fairly frequently, and they can cause Arctic conditions to reach as far south as Florida, which is crazy. The polar jet stream is normally about 50 to 60 degrees latitude, and Baltimore, Maryland is at 39 degrees north. According to the Baltimore Sun in 2014, Baltimore had its coldest temperature in 18 years due to the polar vortex. Temperatures were as low as 3 degrees with wind chills of negative 16 degrees, where the average high in Baltimore during January is normally 32 degrees. So that's like a 35-degree drop from what they're used to. And the coldest temperature recorded in Baltimore from one of these events was negative 41 degrees a bit over 100 years ago. So these events can be pretty significant. The last North American cold wave that happened due to the polar vortex breaking free was in 2019, where many cities affected recorded the lowest temperatures in 20 to 30 years. 22 people died, mainly due to hypothermia, and this is in the modern world with electric heating and being able to predict these cold waves in advance. So in a less advanced society, this would be far more deadly. These kinds of extreme temperature swings are particularly dangerous in places not used to cold weather because these areas won't have the infrastructure and coping strategies built up to handle these extremes. An area that very rarely sees freezing temperatures and instead has clothing, etc. to cope with hot weather will be absolutely devastated by Arctic temperatures. So we are going to mark places on our map that can experience these extremely cold waves every few years. So these are mainly going to be land masses, particularly the eastern sides, between your subpolar low belt and your subtropic high belt, and this is roughly 30 to 50 degrees north-south, and will obviously be more common and more extreme in the poleward ends. So you can sort of see here in this blue kind of squiggly I have on the lower map, that is 30 to 50 degrees north-south, and you can sort of see where my polar front is there. And the blue is kind of just circling, the dark blue circle is circling the eastern sides, and then you can see on the higher up map where I have the cold waves mapped, those are there in blue in those regions. Ocean atmosphere oscillations. We have already covered seasonal monsoons through the process of making our climate maps. These are our AM climate regions. There are other patterns that can take years or even decades to complete a cycle though, not just a season. So ocean atmosphere oscillations are more erratic and unpredictable than the changing of seasons, but they can have large effects on temperature, precipitation, storm patterns. And at their root, these oscillations are strong high-low pressure spots. Some have neutral phases, some are more like a seesaw alternating between events. The unfortunate thing is that we are still learning a lot about these oscillations, still discovering new ones. And we don't know what causes all of them. And what we do know is pretty complicated. Really being able to track these and predict them would likely require a very deep understanding of deep ocean conveyance, temperatures, and depths throughout the oceans, and maybe having like 10 different PhDs. I don't know. These are all things that I don't have. But we're going to take a look at some of the oscillations on Earth and sort of see what we can do. So here's a list of some of the more common, more major, well-known ocean atmospheric oscillations. It's a mouthful. The El Niño Southern Oscillation, or ENSO, is an ocean oscillation caused by the warming of surface waters in the central/eastern tropical Pacific Ocean. And an ENSO event occurs every 2 to 10 years, normally lasting 12 to 18 months. This cycle will involve a warmer phase, El Niño, with reduced rainfall on the western side and increased rainfall on the eastern side, a colder phase, La Niña, with increased rainfall on the western side and decreased rainfall on the eastern side, and neutral years in between. So in warmer years, the ITCZ can be weakened and even reversed, which can impact the tropical and polar jet streams as well. So what exactly do these oscillations cause? We've sort of talked about one example, but they can cause an oscillation can warm the waters and stop upwelling, which can cause fish populations to migrate to better waters. Fishing communities could suddenly find out that there are no fish. Warmer waters can also mean stronger tropical storms and hurricanes. Oscillations can also bring droughts, massive flooding, extreme storms. But what do these mean for our world building? It is unlikely that non-modern civilizations will be aware of this seesaw part of these storms, likely only noticing the more local effects. So some years they might have particularly bad storms, some years might see drought, some years the fish populations might be affected. Copy the dipoles from our ocean circulation maps onto this one in very large ocean bodies and mark the land areas around these dipoles proportionally to the size of the oceans. This is very complex, and I don't understand it well enough to give you an exact process, but it should be good enough to have the rough areas and then flesh it out if needed. But you can see here I sort of marked where those dipoles are on each of my ocean circulation maps and where you're going to see the effects. And then on the right, I sort of generalized it into one map in the green for oscillations. I hope you had fun with this little weather side quest thing that we did today. I don't expect all of these weather types will come into play in all of world building, but I hope it got you thinking about interesting weather and gave you a starting point. If you're trying to think of things to affect your culture and the societies you're building, looking at the areas on your map and seeing what types of extreme weather events would be prevalent there and figuring out ways that your society would explain them to themselves, perhaps through really cool mythology, or ways that they would adapt the way they build their homes, the clothes they wear, the events that they have to prepare for in order to cope and deal with these sorts of events. Very fun. But next, we are going to be doing rivers and wetland biomes, and then after that we will be doing dry land biomes, non-wetland biomes, which will be very fun. And thank you so very much for watching. If you enjoyed this video, give it a like, let me know your thoughts in the comments, and if you have any questions, found any problems, have a request for something to add to the world building guide, please let me know down below, but otherwise, I will see you in the next one.